In the Module 11 assignment, you're going to be studying images of rocks that have been deformed in some way. They've had their original shape changed after they've formed. The branch of geology, the sub-branch of geology, is called structural geology. That studies how and why rocks have been deformed after they already existed. A structure in geology is any instance of a rock's shape being changed, of a rock experiencing some strain, either by faulting or folding or both in some cases. So for example, in this image, you can see how these rock layers have been shifted a number of places and a number of times by a series of faults. Here's one here. Here's a number of smaller ones in here. They're a bit harder to see. Here's one here. We'll come back to this image and figure out what exactly is going on here. There are two main types of structures, two main ways in which rocks can be deformed, faults and folds. We'll cover faults first, show you some examples, and then folds later. Before we get into the details of faults, I want to make sure something is clear in terms of vocabulary associated with faults, namely the hanging wall and footwall. So this upper example is a case of a piece of crust being stretched and a fault forming here, and this is a normal fault. The hanging wall has moved down relative to the footwall, which has moved up. That's what defines a normal fault, and that's what happens during extension. So the label hanging wall is the side of the crust that's above the fault surface. So here's the fault surface, and the hanging wall is the one that's above it. Similarly, the footwall is always the one that's below it. And if it's a reverse fault, the rule is the same. The hanging wall is the one above the inclined fault, and the footwall is the one below. Now the only trick is when you have more than one fault. The hanging wall and footwall labels are relative to the fault that you're talking about. When there's one fault, such as in this upper example, it's pretty clear. The hanging wall here is the one on the right, and the footwall here is the one on the lower left. In the lower image, where there's two faults, we have to be a little bit more careful. So for this fault here, the upper fault, the hanging wall is the one above the fault, and the footwall is the rocks below it. Those terms are relative to the fault we're talking about. For example, here in this second fault here, for this fault, this one here above is the hanging wall, and the one below is the footwall. Notice how this block is referred to both the footwall and hanging wall. It's the footwall when we're talking about this fault, and it's the hanging wall when we're talking about this fault. Those labels are relative to the fault that you're talking about, the fault that you're interested in. All right, let's look at the type of faults that occur. All right, here we are, three main categories of faults. Three main categories. Here's the first two. Normal fault. So this is when the crust is experiencing extension, being pulled apart. And the type of fault that forms is a normal fault. So here it is. And the hanging wall, the one above, has moved down relative to the footwall, which has moved up. Notice how this green layer here, which used to be continuous before this faulting occurred, is now offset down and to the right. The right side has moved down relative to the left side. The reverse fault forms when crust is under compression. It's being squeezed left to right here. So here's the fault that forms. And here, the footwall, again, the one below the fault, has moved down relative to the hanging wall, which has moved up. Notice how the green layer, here it is, which used to be continuous, is now offset, and the right side has moved up relative to the left. Notice in both of these cases, the surface is offset here. We form what's called a scarp, a fault scarp. This is where the surface is offset because this type of faulting produces vertical motion and can offset the surface. In the third type of fault example, it's called a strike-slip fault, sometimes also called a transform fault. There are technically different things, but it's okay if you refer to them as the same. So a strike-slip fault does not produce any vertical motion or fault scarps because it's just side-to-side horizontal motion. This upper example shows an example, the upper picture shows an example of a left lateral strike-slip fault. Here's what left lateral means. If you were to stand on this side and watch the other piece of crust, it would be moving to your left. If you were to stand on this side and watch the other side, it would again be moving to your left. In either case, the other piece of crust, the other side, is always, from your perspective, moving to your left. Similarly, a right lateral strike-slip fault, here we have the pieces of crust moving this way. If I were to stand here and watch the other piece of crust, it's moving to my right. Or if I stand on this side and watch the other one, it's moving again to my right. In either case, in both cases, the other side is moving, relatively speaking, to your right. That's what left lateral and right lateral mean. The San Andreas fault is a great example of a right lateral strike-slip fault. So here it is in California, roughly speaking. So here's California, here's the Pacific plate, and it's moving this way relative to North America. So if you stand in California and look at the Pacific plate, it's moving to your right. Or if you were to stand on the Pacific plate and look at North America, it's also moving to your right. All right, so back to this image. This is a picture of the Moab Fault. It's outside of Moab, Utah, in southeast Utah. And there are a number of features for us to look at here. The most useful thing is to pay attention to this layer here in the middle and see how it's offset. It's offset here, it's offset here, it's offset here, it's offset here, etc. In all of these cases, the right side of the fault has moved down relative to the left, and the fault is also inclined to our right. So because of the angle of the road cut and the angle of the photography, some of these faults look near vertical, but they're not. They are inclined kind of off to the right. You just have to take my word for that, I suppose. This one is pretty obvious here, the angle of it, and this one is inclined to our right too. They're not really vertical, even though they sort of look that way. Nonetheless, what we have here is, so here's the fault I'm talking about right now. I have the hanging wall is the piece of crust that's above the fault. Here's the footwall, the one below, and the hanging wall. This layer has been moved down relative to this one, the footwall, which is moved up, making this a normal fault. All of these faults in here are normal faults. Here's another example of a type of fault also in Utah. What I want you to notice is this sort of whitish or tan layer here, which is thick, underlain by a number of very, very thin layers. This same unit is this one over here, thick tan layer, underlain by a number of thin units. They have been displaced, offset, along this structure here. Okay, so there's our fault surface. Here's the hanging wall, here's the footwall, and the hanging wall has been moved up relative to the footwall, which has moved down, making this a reverse fault. All right, let's talk a bit about folds. Folds are sometimes a little bit easier to identify. And there's three main types of folds. One is called the anticline. An anticline is when the rock layers have been folded upwards, sort of like the letter A. A for anticline here. A syncline is when the rocks have been folded downwards, sort of like a sink shape. Syncline for sink shape. Sometimes you'll find rock layers which have both, which have started out flat, but you find them like I'm drawing here, that have both anticlines and synclines. Sometimes you'll find cases where you just see a single anticline or a single syncline. You can have both, you can have either. There's no reason to have one or the other. It just sort of depends how they were deformed. Folds form in rocks when they are warm enough that they can flow very slowly, and they're too warm to build up enough stress to break. So folds form relatively deep in the crust, whereas faults tend to be much shallower, where the rocks are colder and are more brittle and intend to break instead of folding. So an anticline and a syncline, sometimes together, sometimes separate. The third type of fold is called a monocline. Anticlines, for example, an anticline, here's a rock layer, finish this. There's the anticline, there's the syncline. An anticline has two limbs that are the left side and the right side, and a syncline has two limbs, the left side and the right side. A monocline is just one of those limbs, hence mono, one fold if you like. A monocline is where you have flat-lying rocks that are then gently folded and flat-lying again. So here these dip down and to the right. But they don't always have to be down to the right. I've flipped this image over just to illustrate that the fold could look like this. It could be folded up and to the right. The key is that they're flat-lying on either side and gently folded in between. Flat-lying, folded, flat-lying. Okay, some examples. This is a famous road cut. This is where the mountainside has been cut away in order to put the road in. You can see this car down here. These horizontal lines you should ignore. These are terraces, the way they cut the hillside back farther and farther as they go to the top in order to make that slope stable. So ignore those. But you can pretty clearly see how the rocks have been folded in this way, making this a syncline. All right, so back to the Grand Canyon. Grand Canyon has a number of examples of monoclines. So I'll show you two examples here. This is on the north rim of the Grand Canyon on the east side, looking to the north more or less. And we're standing at Marble Point. It's not really made out of marble. It's made out of limestone, but nonetheless, it's called marble. And this is a great example of a monocline. Specifically, it's called the East Kaibab monocline. And notice how we have flat-lying rocks off to our left. These are the upper layers of the Paleozoic sequence at the Grand Canyon. We've heard about this before. This one here is the Kaibab limestone, that's topmost layer in the Grand Canyon. Okay, and it's flat-lying off to our left. But as we move to the right, to the east, you can see how these rocks are gently folded. We have to go behind Marble Point here. And then off to the right, they're flat-lying again. So the top layer here, the Kaibab limestone, is flat. Some of it's been eroded, but it's gently folded. And then it's flat-lying. And the uppermost layer out here is again the Kaibab limestone. So the rocks on the left have been uplifted a few thousand feet relative to those on the right. But the only record of the rocks being deformed is roughly, in the middle here where they've been gently folded along this monocline. They're flat-lying to the left, to the west, and to the right, to the east. Another example from the Grand Canyon of a much more subtle monocline is called the Crazy Jug monocline. So we're on the south rim of the Grand Canyon looking towards the northwest. And here we have these layers out here on the left are the uppermost layers of the Supai group, sandstone mainly. And they're flat-lying. Some of them have been eroded away here. You can see just this little bit here, for example. And here they are off to the right, also flat-lying, but in the middle they've been gently folded. And it takes kind of a trained eye to see that, but this is exposed in a few places, a few different viewpoints. If you look carefully, you can see the gently fold of the Crazy Jug monocline. Off in the back, there's another example of folded rocks. For example, this here is the Coconino sandstone, which has been gently folded, and then that fold ends along this fault. This fold is a result of activity on the Muab fault, which sort of runs through the back part of the picture here, where these rocks have been moved up in the past relative to those on the right. And it's the motion of those rocks sort of getting stuck on this fault, which resulted them getting bent down over time. This fault has since reversed its sense of motion. It used to be a reverse fault back during this period called the Laramide orogeny, roughly 70 to 40 million years ago, when the western U.S. was under significant compression. But since then, it's changed its behavior. because now the southwestern U.S. is under a period of extension called basin and range extension, which in the Grand Canyon has been occurring for about the last 15 million years. So this fold occurred when these rocks were being uplifted, but now they're actually on their way in the other direction. Motion on this fault is very, very, very small compared to many others in the western U.S., but nonetheless it's still an active feature in the landscape. All right, there you are. There is the intro to the assignment 11. When you're done, please send it to the assignment 11 Dropbox. All right, let me know if you have questions.